Hey there, Math 125 fans. We're going to talk about improper integrals. This is currently at section 7-8 of the book. You know, if additions change and you're watching this video in the future, these are things where you have some sort of asymptote or something where you'd like to know what happens in the long run. Most worries I get from students on this have to do with the fact that they're worried about limits. I have a lot of supplemental material on that. But honestly, if you've done the homework, you realize that there's really not very many challenging limits in there. Now, the most important step is the first step. We are trying to get you to understand the process here. You never plug in infinity to something. I think students seem to have a misconception about what infinity is. It's not a number. You can't do things like infinity minus infinity equals 0. Infinity minus infinity is 14, everyone knows. If you go for a run and the person in front of you is 14 feet away from you and you both run forever, infinity minus infinity is 14. We call it an indeterminate form. So you can't think of infinity like a number. You have to analyze it. And that's the point of these questions. So there is an asymptote here as you go to infinity, kind of an interesting looking function, but that's a side topic. So this is what we're looking for. You're going to pick some symbol. I like to use T if it hasn't been used yet. And you're going to write this. And then the rest of the problem doesn't really have much to do with limits. It's just at the very end, we'll have to make a conclusion. So I think students make this section worse than it is in their mind. So I'll put these little parentheses here just to emphasize the point. So we are now going to figure out what this is, which is just another chance for us to practice integrating, which is good. And then at the end, we'll try to figure out what happens in the long run. Okay, but this is a very important step. So I tell them I'm going to take off a lot of points if they don't write that limit, because that's the idea of the whole section. Okay, this integral looks terrible to me. And the moment I say that, I know the method. The method is substitution. What are we going to pick for substitution? I would pick the inside. Hopefully this is coming into focus. So the derivative... This overlaps with what I just finished in my series on how do we integrate. Okay, let's solve for dx. Dx is going to be negative pi. You know, at some point, I really should rewrite this as negative pi. Negative exponents are fine for derivatives, but tend to lead to confusion when it comes to algebra. As I was about to make a mistake there, I need to move it to the other side, so I'm going to write negative e to the x over pi du. Okay, let's substitute everything in now. So this is going to become the integral. 0 is going to become, well, let's see what happens when we plug in a 0 here. Oh, it's 1, so it's just going to be a pi. What happens when we plug in a t there? Well, it's not pretty, but we can do it. Good. And then we have sine of u. And then we have, unfortunately, this e to the x, which bothers me. Don't move on unless all the x's go away. And then we're going to replace the du by negative e to the x over pi. I put the parentheses because I was afraid I would think I was subtracting. Okay, I think I've successfully substituted everything. And hooray, the x's go away. Good. If that hadn't happened, I would have been worried. This is still the limit as t goes to infinity, but that's something we're going to worry about at the end of the problem. So you can see these really just become problems where you get to show your integration skills. We can factor out a negative 1 over pi, and then we're just integrating sine, which is going to be negative cosine, so it's going to make this positive, cosine of u. And you don't need to switch back. This is one of the huge advantages of changing as you go. And then you substitute everything in. So the limit, again, we don't worry about that limit till the end. We first need to find the pattern for the area. Now, a small comment. When I know I have a constant there, I sometimes pull it all the way out. That's not that important. I don't even know why I just said it. Minus cosine of pi. But cosine of pi, I know, is negative 1. So it's going to be minus negative 1. Okay. So now we are ready. Well, we could still go a little further, but I think we're ready to say what happens as t gets larger. This requires, and the one thing about limits is, especially infinite limits, is you have to know how functions behave. So in order to finish this problem, you have to know how this function behaves, which is a big important skill. If you don't, I have a thing on my website about the graphs you need to know, but you should know that's exponential decay. So that means that in the long run, this is going to approach 0. So altogether, this thing is going to approach cosine of 0 plus 1. And cosine of 0 is 1, so it's going to be 2 over pi, and we would say it converges. Okay. And I think I've written everything. Great. Wonderful. So there's an improper. Let's do another one. So here's from spring 2017. You can go back and watch that earlier part. So here we go. Let's rewrite it as a limit. Step 1. T goes to infinity. The integral from 1 to t. I'm going to rewrite this the way a calculus student would write it, which is times x to the negative 1/2. And then it becomes an integration problem. How do we integrate that? What method is good for products, logs, and inverse trig? Integration by parts. So that's my first thought. It probably also works to substitute for the square root of x and give yourself something new, but I think no matter what, we're going to end up doing some sort of integration by parts. So again, the only thing you can't do is sit still. You should either be doing a substitution or integration by parts, but the fact that there's a log here screams try integration by parts and put log there. Okay. dx, this is 1 over x dx. We integrate here so the power goes up 1 and there's a 2 out in front. And then we have the limit as t goes to infinity. Bounds don't change because we're not actually changing the variable. We smush these two things together. Now at this moment I'm going to rewrite it as the square root because I know I'm about to plug in numbers. So I'm about to become an algebra student again. Minus the integral, and I'm going to smush those two things together, which becomes 2x to the negative 1/2 from 1 to t. I know that because I had x to the 1/2 over x when I smushed those together. Anyways, okay, so then we evaluate, plug in a t, plug in a 1. We have the limit as t goes to infinity of 2 square root of t log of t minus 0, because log of 1, minus, this is going to become 4x to the 1/2 from 1 to t. And that's going to be the limit as t goes to infinity of 2 square root of t log of t minus 4 square root of t minus 4. Okay, so now we're finally at the point where we get to consider the limit, but we're considering the limit for this thing. So this once again goes to, do you understand what the log looks like? Do you understand what the square root of t looks like? What about if you multiply them together? And you should already know that the log function as you go to the right goes to infinity. So this is going to infinity. You should also know this is going to infinity. Both of these things are getting larger and larger. And then we're subtracting the square root of t. So you go, well, that's infinity minus infinity, so must be 0. Uh-oh, you got to be careful with that reasoning. So this is one of these situations where I have to pause myself and say, okay, it's clear to me this is going to infinity, but this is also going to infinity, so what am I going to do? And the answer is you need to simplify it in some way to help your analysis. You can't just say infinity minus infinity is 0. Okay, so let's see what happens. T goes to infinity. Now I'm going to try to group these together to help my analysis. Can I? Oh, I can. So let's distribute the minus. I should have already done that. I'm going to make this a plus. And what do they have in common? They both have a 2, but that's less exciting. You see, that's a 4, but I'm going to factor out 2. And the square root of x. So I'm going to do 2 square root of t. And then I'm going to write log of t. And then I'm going to write minus 2 plus 4. Okay. Let's go. I'm going to go down here and look down at it. I don't know which way I'm supposed to look. there it is. I have to learn how to point at things. See, point the wrong way. Here, click on this. Okay. I'll never be good at that. All right, so here we go. This goes to infinity. This goes to infinity. And now I can see I am multiplying two things that are getting really large. And so this whole thing goes to infinity. And we say diverges. So ultimately, this is growing much faster than that. But it helped me to put them together to make sure that was true. Okay, I think I'm just going to do one more. I'm getting sleepy here. This one's improper for a different reason. And this one would be easy to like miss if you I usually tell students, when you see something like this, you first ask the person who wrote the question, did you mean this to be improper? Because the problem is 1. You can see a 1 there. So what do? We have the integral. We have a 4, and we have this problem at 1. So how do we say this? And this always surprises me that we end up having a long discussion about this in class. But if you're doing an integral from 1 to 4, and you have some function with an asymptote here, and that's not necessarily the right picture, I'm just making up a picture. In fact, this one, no, it's positive. And there's an asymptote right here. And you're standing in here and trying to do the area, trying to paint it all. Are you approaching 1 from numbers that are slightly bigger, like 1.001, or numbers that are slightly smaller? Slightly bigger. We have a notation for that. 1 with a plus means numbers slightly bigger than 1. 1 with a minus means numbers slightly smaller than 1. Sometimes I think students maybe jump into Math 125 and they didn't take a full 124 with one-sided limits, and they get really scared about this. Doesn't really affect very much. So it's not a scary thing, but we're approaching 1 from the positive side, from the larger side. If you want to, it's bad. I feel bad just giving someone a process, but if it's the bottom one, you're going to have a plus because you're approaching from above it. If it's the top one, it's going to be a minus. It really is such a small thing, but I always get a lot of questions about it. Okay, so now we need to integrate. How do we integrate that? It looks weird. Part of the reason it looks weird is because that's square root. So what are we going to do? So I am tempted to pick this because it's all the stuff that's on the inside and it's on the bottom. It probably also works to pick the square root of x. Now a small note, I'm going to use our little maneuver, see my last video, where I'm going to solve for x first before I take the derivative. That is not necessary, but I think it saves you like half a step. Okay, so what's this become? The limit as t goes to 1 from the right of the square root of t minus 1. I got that by plugging this in. Square root of 4 minus 1 is 1. 1 over u with a 1/2. And then dx is 2u plus 1 du. So let's kind of see where we're at. Let's pull this 2 out. Let's do the limit as t goes to 1 of the integral of the square root of t minus 1. And I'm going to zoom, do two things to make us, this is where we're at. And then I have u plus 1. And in my experience, often on a question like this, students get here and then they're just lost. But it doesn't have to do with the improper. It has to do with they don't know how to integrate that. This is another one of these situations where it looks messy, but actually it's not. And when you get in a situation where you're like, this looks strange to me, I don't know what to do, it's either substitution or simplification. Now, substitution will work, but simplification works better. I think this is just an uneasiness with fractions is why I see this error a lot. But those things are the same. So this was actually already in a form that you could distribute. I think when you have a number on the bottom, students don't think about distribution, which is always interesting to me. There's something about that that they're worried about. They've been burned in the past by bad fractions. But that's legal. Okay. Anyways, this is 2, the limit as t approaches this. I'm going to rewrite the rest of this. T minus 1 to 1. This is going to become u to the negative 1/2. No, u to the positive 1/2. See, I check everything as I go. That's what you're trying to learn to do. U to the negative 1. And even then, I still make errors. I always tell students I wouldn't get 100% on these tests because I'm too prone to errors. Okay? But I have different priorities. All right, 2/3 plus u to the 1/2, 2, evaluated from square root of t minus 1 to 1. And then we plug everything in. When you plug in a 1 everywhere, you get 2/3 plus, I'm plugging this one in, 2/3 plus 2, all right, minus 2/3, and you're getting this big mess, but I'll worry about interpreting it in a second, plus 2 times the square root of t minus 1, square root. Okay, now is the one moment where we have to do a limit. So I always tell students, even if you said, I give up on limits, which I hope you don't do, you would get 90% of the problem. So these improper problems really just become more chance to study your integration skills. Okay, as you approach 1, this is a finite limit, so it's a little different. We do try to plug it in. And in this case, it's continuous. It is allowable to plug it in. There's no error there because you're just getting positive exponents. There's no issue. And so we have our answer. It's 2 times 2/3 plus 2 minus 0. And so altogether, let's see, how would I want to move forward? Funny little thought, just to do it in a weird way. I'm going to factor out a 2 to make it a 4, and then it's 1/3 plus 1. There, I just lost everybody. So this is going to be 4 times 4/3, 16/3. Hooray. Yep, that matches, it converges. All right, let's end that there. Hope that's helpful to you. I have plenty more practice on my website.